Okay, so hello everyone, and thank you for showing up. Also, Sasha, thanks for inviting me. So I'm going to talk about a case in a northern North Sea rift where in a large scale, so we have a multi-rift basin, while some part of the basin is not rifted in several phases. Yeah, so in a larger scale, we have a multi-rift system, but some part of the basin has only experienced a single rift phase. So I'm going to show some results and compare these to single phase rift versus the multi-phase rift in terms of the basin geometry and the fault kinematics. So this is the work that I've been doing previously, basically at the University of Bergen with some collaboration with Imperial College, Manchester, and some and the Norwegian Science Foundations. So the study area, so we are looking at the northern North Sea rift. So what we see here on the right-hand side is mainland Norway that shows some Caledonian remnants of NABs and allochthonous units and some para-autochthonous units below. And to the left, so we have the UK and also remnants of Caledonites. And in between, we're developing a North Sea rift system basically, and we are looking at the northern part of the North Sea rift, where it has experienced several, at least two rift phases. So the rift itself developed above a very heterogeneous basement. So we have several orogenic events prior to rifting, and also during the early to middle Devonian, we have a post-orogenic extension creating some some basins, basically Devonian basins. That is because of the reactivation of pre-existing shear zone and the column and other existing features. So pre-rifting configuration. So we have as I said, several orogenic shear zones, as we see here. So we have some NABs, remnant of NABs, para-autochthones and continental basins like this, shown as yellow here. These are the post-orogenic extensional basins. And towards the northern North Sea rift system, so there are some of these pre-existing structures are reactivated. Some of them are cross-cut by the rift faults, and those ones that are reactivated, just localizing the strain along those along the structure. So there's a complex pre-rift history in the northern North Sea, and but we're going to focus on the rifting itself. So the study area, so here is in the offshore of Norway. So this is Western Norway, and here we see the Norwegian part of the northern North Sea. And the map that we see is the base of the rift. So the base of the first rifting episode, which is the Permo-Triassic rift. So we call it RP1 as a rift phase 1. And then the second rift has occurred later in the Middle Jurassic to early Cretaceous time that overlaps the first rifting event. So the entire basin has experienced at least two rift phases, but to the southeastern part of the northern North Sea, so here, as I showed by the dashed blue line, so it's the Stord basin, which only experienced a single rift phase, so which means the only rift phase one has occurred in that area. So we're going to look into the details of the Stord basin. So the Stord basin, again here, so we are looking at this cross-section, northwest, southeast, shown here. And the Stord basin is located in the southeastern part of the profile. So we see a very thick interval of the early Syn-rift and late Syn-rift, which are Permo-Triassic, and then into the post-rift or inter-rift interval here. Towards the northwest, so we have a South Wackengraben area here, which records basically both rifting phases. So if you look at the stored basin itself, so we have two major basin bounding faults. So the Oygarden fault to the east and the Utsira fault to the west that are bounding, and then some major kilometer scale normal faults in the basin center. So we're going to look at the Permo-Triassic development of the stored basin now. So the map that we are looking at here is basically a time thickness map. We used, I should have mentioned earlier, so we used a very dense grid of the 2D seismic, which are the space like about 3 to 5 kilometers away from each other, and extensive well exploration production wells. So which makes the North and North Sea a very good case study to look at the rift basins. So the map that we see here on the left-hand side is a time thickness map of the early Syn-rift during the Permo-Triassic. So basically we are looking at this interval that I'm highlighting by these red arrows. So what we see, so the main depot centers are developed in the center of the basin, in the central part of the basin, and also are more or less fairly distributed along the basin bounding faults here, and also in the central part of the basin where we have smaller scale faults. So scale here is about 50 kilometers. So we are looking at only major large faults. So as we move up, so during the latest stages of Syn-rift 1, so the general thickness, reduces. And so now it seems that the main depot centers are localized along the basin bounding faults. So, and this time structure, a time thickness map, is the interval that I show with the yellow arrows. And the section location is by these gray arrows. Basically what we see during the early to the late Syn-rift, so the rift or the depot centers are migrating towards the basin bounding faults, and are so those faults are actually accommodating more amount of deformation during the latest stage of Syn-rift. So in terms of the faults, so the central these faults that develop in the central part of the basin are shortened or smaller, and but towards the southern part of the basin, so we develop a newer faults or fault segments. So now if we move on during the second rift phase, so basically the first map on the left-hand side, again is a time thickness map. During the second rift phase, the Syn-rift of the second rift phase, so I show the interval by the red arrow here. So what happens here, so basically the stored basin enters into the tectonic quiescence period, and the thickness changes that we see here is related to the delta progradation and clinoforms that fills up the basin. So tectonically, basins goes into the quiescence, so no more tectonic activity, and then receives the input from the Norwegian mainland. And then during the lower Cretaceous, then a second deltaic system develops farther north, and then later during the upper Cretaceous, basically we fill up the basin, and the thickness difference is less than 200 milliseconds here. So in terms of the strain migration during these Permo-Triassic rifts, so if we look at the fault throw versus distance plot that we see, okay, it might look a bit busy profile. Anyway, so here in the right-hand side, so this is the Oygarden fault system, the eastern bounding fault, and we are looking at different segments. Yeah, so the red plot here, the graph here, it corresponds to this is a third segment of the Oygarden fault. So mainly what it shows is that we are during the first rifting phase, we have about 2 to 3 kilometers of throw along this fault. So basically towards the northern part of this fault segment that gradually decreases towards the south. So the entire fault in general shows a progressive southward decrease in amount of throw, but each individual fault segments also shows variations in between. Towards the towards the western side of the basin, so the activity is about 2.5 kilometers here, but the difference is that during the secondary phase, so as we see here, so the smaller or the second graph for each fault segment. So the amount of fault displacement is higher towards the west in compared towards the eastern side of the basin, vice versa to the first rifting phase. Another interesting point is that the faults that have been developing in the central part of the basin are now abundant, so they are no more active. And as we see by the fault graph, so the F1 to 4 are corresponding from 1 to 4 from north to the south. Yeah, so two main points. So during the secondary phase, so the faults that were in the center of the basin are abundant, dies out, while the basin bounding faults show very limited amount of activity. And the western side of the basin shows more activity during the secondary phase. So now if we look at
just a quick comment, you're at 11 minutes now.
Okay, so now if you look at the general North Sea, so in a larger scale, so as we see, so we just saw the Stord Basin here in the southeastern. So during the first rift phase, so the main axis was around the Stord Basin, Horda Platform, and East Shetland Basin. While during the second rift, so the rift axis migrates towards the west here in this case, and lines along the Viking Graben in different segments. So on this thickness maxima that we see here is related to this delta X system developed during the second phase. So what's interesting is that so while we are ongoing rifting along the Viking Graben, so we have a kind of passive margin like delta development towards the east along the Stord Basin. So now we can plot so displacement versus length, and to look at the rift phase 1 faults versus rift phase 2. So as we see, the blue area here are the rift phase 1 faults, and the pinkish area is the faults that were reactivated during the secondary phase. We see that so they are during the secondary phase, they are under displaced, and they show one order of magnitude less displacement in compared to the rift phase 1 faults. So now if you compare, well, we can also compare the amount of extension during the rift phase 1 and rift phase 2. So this map shows a compilation of RP1 and RP2 in the northern North Sea. So here in the Stord Basin, so we record a 1.55 of beta factor or the stretching factor during the first rift, which is the highest amount than the other areas. But during the second rift is almost quiescent. Yeah, so no more activity as the time thickness maps are suggesting. So this amount of activity or extension has produced some amount of melt, and the magmatism that has been shown towards the northern part of the Horda platform. So where we see like extension amount of extension factor of 1.4 there. And there, so they were have been shown before by Brona et al. That there are some possibly some melts crystallized in the lower crust. So now, if you look at the Stord Basin in this area, so having the higher amount of extension, also having some Permian rift, Permian dikes in the onshore, and then so we suggest that we might also have some melts below the Stord Basin. But unfortunately, the quality of data was not enough to image that. And just for a conclusion, so I leave the concluding points here, and then that we have more time for questions. Thank you.
Thanks a lot. Indeed, we have a few minutes for questions. Gary.
Hello, very nice talk. I think you've shown very well the fault control on substance, on Syn-rift subsidence. What can you say about what actually controls the post-rift subsidence over the North Sea in general? Because it does seem to be totally unrelated to the brittle deformation of the crust.
Complex and interesting question. So the post-rift, so you mean the post-Jurassic Cretaceous rift or the post-Permian rift?
Well, either, but I think you can't separate those out easy. So let's just sort of talk with the Syn-Cretaceous and post-Cretaceous substance, the regional substance that's not fault controlled.
No, so I think could be related to the thermal subsidence during the post-rift that we have. Yeah, so the entire basin subsides because of the downwelling below the rift axis, then just opens up for more accommodation. Yeah, so that for the thickness that we see in the Cenozoic section. That would be one of the factors, but also I don't know. So maybe the onshore uplift also plays a role. At the same time, just adds on into the thermal subsidence during the post-rift.
Just for completeness, I mean, thanks for that. But for completeness, the amount of extension on the faults, the heave is relatively small. It's localized and small, and yet we still have very significant regional subsidence. I think, again, we sort of have a real disconnect with a very nicely showing brittle deformation of the crust and still no real understanding of what's driving the regional thermal subsidence, if I might say.
Yeah. I mean, so 1.1 limitation of calculation. So when we calculate this amount of extension by summing up the heaves, is the subseismic, the amount of subseismic deformation that is not recorded by the fault heave, especially when working with the seismic data. Yeah, so we might account for, I don't know, 30 or to 40% of underestimating amount of extension. So I mean, so that is also an important factor to keep in mind.
Thank you.
Okay, Fullerin, you raised your hand. This is a question, right?
Hamed, thank you very much for the talk. I did read that paper and I enjoyed reading it. So this is my question. You did imply that the early phase magmatism probably had something to do with the failure or abandonment of the stored basin and migration of the stream towards the west. And I'm wondering how that is so. You know, you have both the South Viking graben active at the same time, you know, during RP1 with the stored basin, and you could also have had underplating beneath the Vikings graben, right? But then for some reason, only one was abandoned. Mm-hmm. Can you shed more light on that, or whatever you think that? Because I'm really trying to see how the magmatism could have influenced the outward migration of stream from the stored basin.
Yeah, so we hypothesize that. I mean, so it's not clear. Yeah, so there are some models that trying to explain this rift axis migration. Yeah, so what we see in the stored basin is basically we have a very ultra slow extension. Yeah, so we have a rifting that course almost 40 million years long, and then with looking at the amount of extension, so we are almost about 1 millimeter per year of extension. So this is basically an ultra slow extension. Yeah, and then and also if we add on some magmatic underplating and also tectonic quiescence between two rift faces, so these three factors together might have influenced this rift axis migration. But at the same time, so the amount of the velocity of extension and the magmatic underplating might be the same also in the South Viking graben, as you mentioned. But the point is that so we don't know how fast So we don't know if the velocity of rifting is the same across the rift. Yeah, so we might have some faster rifting or more localized or the shorter time span of rifting along the southward working graben that is different from the stored basin. So we don't know. So so the south working graben is very unknown in comparison to the rest of the northern North Sea. Yeah.
But the South Viking graben also went through quiescence, right? There was that, So again, I do appreciate your comment. I know it's still an open question. Yeah. I'm just very interested in that hypothesis, but it's totally okay if you don't.
I see your point, and to be honest, I don't know. Yeah, so I just try to think of comparing the stored basin, which is like 50 kilometers east, and then the northern North Sea, the northern Horda platform and other areas. So there are some differences, but are those differences really causing this rift axis migration or not? I don't know.